ESO telescopes are being used to search for the subtle signs of magnetic fields in other stars, and even to map out the star spots on their surfaces. This information is beginning to reveal how and why so many stars, including our own Sun, are magnetic, and what the implications might be for life on Earth and elsewhere in the universe. In Southern Observatory. More than 400 years ago, Galileo Galilei became one of the first astronomers to note that the Sun's surface exhibited dark imperfections, now known as sunspots. What Galileo didn't realize at the time was that these dark spots were a sign that the Sun is a magnetic star. Sunspots appear dark because in these regions, the strong magnetic field limits the transportation of heat to the surface. This process makes these locations much cooler and thus darker in appearance than the surrounding brilliant surface. As sunspots develop, the magnetic field increases in strength and complexity and becomes increasingly tangled. Eventually, for some sunspots, the magnetic field snaps and, in an instant, the energy it holds is unleashed in a brilliant and violent flash. Emerging as solar flares and solar storms, this energy is sent hurtling directed at Earth. This energy, arriving in the form of a stream of charged particles, is mostly deflected by the planet's own magnetic field. But some of the charged particles get through and create beautiful aurorae in the northern and southern polar regions. But beauty here can also signify danger. Solar storms, if powerful enough, can in turn spark geomagnetic storms on Earth, capable of destroying satellites, interfering with air traffic communication, and even crippling power grids. In a technological era, this threat is reason enough to study solar magnetism. The Sun is not unique in being magnetic. Most stars in our galaxy harbour a magnetic field of some kind. Although we don't fully understand the processes that create our own star's magnetic field, other Sun-like stars are expected to have similar properties. Stars, such as those that are much hotter and more massive than the Sun, may be very different. But what is known is that solar flares and storms can impact life on Earth in a profound way. Measuring a star's magnetic properties can help astronomers to evaluate how hospitable an orbiting planet might be for life. The magnetic field of a star can be measured through what is known as the Zeeman effect. Chemical elements produce narrow dark absorption lines in the spectrum of a star. When a magnetic field is present, these lines split into triples or even more complex groupings. This splitting can be measured and used by astronomers to gauge the strength of the magnetic field. But the Zeeman effect leads to an additional effect. The starlight becomes polarized. This polarized signal is the vital clue that can be used by astronomers to spot the presence of a stellar magnetic field. ESO's telescopes and instruments, such as FORS on the Very Large Telescope, are equipped to detect polarization. They are powerful tools with which to measure stellar magnetic fields. One of these instruments is HARPS, the High Accuracy Radial Velocity Planet Searcher. It's located at ESO's La Silla Observatory in Chile. HARPS very accurately measures the Doppler shift of stellar spectral lines to look for the subtle signatures of exoplanets. But HARPS can also measure the polarization of spectral lines to detect stellar magnetic fields. For some stars, this spectrograph can measure thousands of spectral lines simultaneously. helping to detect signals from even the weakest magnetic fields. By observing a certain star several times while it rotates, scientists can now use these polarization measurements to create actual maps of the magnetism-related star spots present on distant images stars. Remain impossible to obtain directly with large telescopes, as almost all stars are simply too far away to be seen as anything more than points of light. But thanks to the huge amount of information contained in the polarized signals, we can uncover a great deal about stellar magnetic fields, revealing valuable data that would otherwise remain hidden. Astronomers have found that most stars are magnetic, but in very different ways. So different processes must be at work to generate and sustain these magnetic fields. We now know that these magnetic fields in turn have a big impact on how stars behave throughout their lives. They play an important role in the complex processes of star formation, and at the other end of stellar lives, they are vital to explaining the bizarre behavior of gamma-ray bursts, pulsars, and, most extreme of all, magnetars. Astronomers are now eagerly studying stellar magnetic fields of rocky exoplanets around them. A star's magnetic field can greatly affect the amount of radiation reaching a planet's surface. Intense flares on stars produce ultraviolet radiation that is hazardous to most forms of life, both primitive and advanced. Magnetism has effects throughout the universe, from the Earth's surface right out to the most distant exploding stars. Polarization measurements help astronomers to understand the magnetic properties of our own star and all the other stars in the universe. ESO's La Silla Observatory on a moonless night, deep in the Atacama Desert of Chile. It should be very dark, but strange green and red colors can be seen to shimmer in the sky. What are these mysterious glows? And why do they seem to be getting more frequent? The European Southern Observatory. The Sun is constantly showering the Earth's atmosphere with radiation at many different wavelengths. Solar ultraviolet light destroys oxygen and nitrogen molecules during the daytime, and this triggers a chain of complex chemical reactions. As a result, new molecules like ozone are created. When night falls, some of these molecules take part in further reactions and collisions, causing them to radiate light. This process is known as chemiluminescence, seen in the night sky as an eerie glimmer, an effect called airglow. To the naked eye, the colors of this airglow are invisible, but sensitive wide-angle photographs show the fine green or reddish tinges of this phenomenon. Sometimes, airglow appears to be just a faint tinge of color on the horizon, but it can also be a menagerie of changing colorful shapes. The green layer of airglow lies about 100 kilometers above the ground. Here, it is seen from the International Space Station. But there is also a much fainter, reddish tint of luminescent air to 300 kilometers of 150. The extent, color, and brightness of the airglow vary with time and place, and are influenced by many different factors. For example, the red glow tends to be brightest at the start of the night, and around midnight and later it can be very weak. And Cerro Paranal, home of the VLT, happens to be located below what is known as the South Atlantic Anomaly. Here, the Earth's protective magnetic field which prevents particles from reaching the surface, is reduced, and more particles from the Sun hit the atmosphere. This can lead to brighter airglow. Airglow can also appear in strange formations. They are formed by alternating air pressure layers that can grow with height as the air thins. We understand what causes airglow, but why are we seeing more and more of it in photos taken at ESO sites in Chile over the past 5 years? Has airglow become more common? Could it be caused by some global change in weather patterns? The answer is not clear. The recent rapid development of digital cameras seems to play a role, allowing fainter details to be picked up in the night sky more often. But identical cameras have revealed dramatically different skies just weeks apart. Since airglow is triggered by ultraviolet radiation emitted from the Sun, changes in solar activity can have a big impact on the brightness of the airglow. The Sun cycles through periods of low and high activity every 11 years, and what it seems is the main reason for the recent increase in airglow. The most recent cycle of high solar activity, coinciding with more sensitive digital photography, has provided our first detailed look at this strange phenomenon. Airglow can be beautiful and photogenic, but it also affects scientific observations. Certain kinds of airglow give rise to background patterns in near-infrared images from the VISTA telescope as the airglow structures move in between exposures. One way or another, it's a feature of the celestial display over the ESO sites. One of the darkest places on the planet, even the sky is never completely dark.